Hey, let's take a look here at section 5.1, function composition. Okay, so we start off with a definition here of what a composition is. So suppose f and g are functions. All right, we know what functions are. The composite of g with f, denoted g composed with f, is defined by the nice little formula here. G composed with f of x, that is going to be equal, well, we're just going to put the function f inside the function g, wherever we see x in g. Okay, so let's look at a little picture here. So what we started with when we started talking about functions, we started talking about maybe like a little function machine here, right? I would start with my x value, and I would put that into the function g, and then out it spits here g of x, right? For example, maybe if I have g of x is 2x, right? I would take whatever x value it is, and then the function g is just going to multiply that number by 2, right? And then it's going to spit out that value right there. Well, what a composition is here, we're going to now put this function inside of another function. So maybe there's a function here, f, and I'm going to put that in there. And then the output from this guy is going to be f of g of x, right? Because that's the input into the next function is a function itself, right? And I know, the notation here is a little backwards, but the idea is the same, right? We could just as well have, put an f on this one and a g on this one, and now this is g of f of x, right? So going on our little journey here, following where x goes, we start with x. So we start with the number, whatever number that is, and we put it into the function f, and then whatever comes out of the function f is going to go into the function g, and out spits g of f of x rather. Oof. Okay, so now we've got this little piece at the end. This is where our trouble is going to come. We have to make sure that x is in the domain of the first thing, right? Following along where x is going along its little journey. The x value is going to go into the function f. So we need first and foremost that x value to be in the domain of f. And then on that next layer, f is going into the function g. So we need to have f in the domain of the function g. So this is going to make sure that everything is defined, everything's has a value. Okay, we'll get to this bit a little bit later, but for now, let's just look at a couple examples here. So if we have listed out a bunch of ordered pairs, right? Because that's all functions are; they're just sets of ordered pairs. So if we have them explicitly listed, we can find these things. So let's find g of f of 1. So this is g of f of 1. So first we can find f of 1, right? So f of 1, here's the function f. If I want f of 1, I'm going to go to the x value 1, right? There it is. And the function value is that y value that goes with it, so 3 here. So this is going to be g of 3 because f of 1 is 3. All right, then we go to the function g. So now we're looking at g. I'm going to switch this back to green here. So we're going over to g, and I want g of 3. So then I would find 3 in our ordered pairs. Well, there it is. So the function value there is 4. So g of f of 1 is 4. All right, and then we can do this one. So f of g of 1. We're going to do the same thing. So first we're going to find g of 1. So going to the function g, where x is 1, that function value would be 2. So we got f of 2. And then I'm going to go to my function f and find x equal 2 right there. And our function value is 1, that y coordinate. Right, and now something inherent in these ordered pairs, all these ordered pairs are x's, comma, and then g of x, whatever that is. All of these ordered pairs are x, comma, f of x, right? Because our y coordinate of our ordered pair, that's always the function value. Okay, good. And we can do f of 1 as well. So f of 1. So f of 1 we found earlier was 3. So we got f of 3. And then f of 3 we see, right, there's that ordered pair, so that is 4. Okay, we got it. How wonderful. So yeah, if we're given explicit lists of ordered pairs, all we're doing is just finding the y value that goes with it. Okay, so we're not going to see these all that much in practice, but there are going to be a few homework examples that involve stuff like this. What we're going to be more likely to see are explicit functions here, right? So we can do the same thing with this, right? If I want g of f of 1, this is g of f of 1, right? So I want now the function z evaluated where the input is f of 1. So this is g, and then I can put f of 1 inside that parentheses. So f of 1, I would put 1 wherever I see x in the function f. So this is g of, what is this, 1 minus 4 is negative 3. So now I go to the function g now, and I put in negative 3. So we got 2 minus square root of negative 3 plus 3. So that is 2 minus, well, 0, so that's just 2. Okay, cool. So g of f of 1 in this case here is 2. All right, let's do the other way. F composed with g at 1. So we're going to put g of 1 inside of f. We can find g of 1, right? F of g of 1, we're going to put 1 in place of x on the function g. So we got f of, we're just evaluating the function now, right? 2, and then we have 1 plus 3, that's 4. Square root of that is 2, so 2 minus 2, so that's f of 0. And we're just going to put 0 in for x in the function f. So we got 0. All right, one more. We want to do g of 6. All right, well, yeah, same thing here. Let me put some lines here between these examples. If I want g of 6, first we're going to put 6 into the function g. So we got 2 minus square root 6 plus 3, right? We put 6 wherever we see x in the function g. Now we can evaluate what's inside there. So I got 2 minus, what is this, square root of 9, that'd be 3. So this is g of negative 1. And now we can put that into the function g. We would have 2 minus square root negative 1 plus 3. So we have, what is this, 2 minus square root of 2. And that's it. All right, so we're just, repeating the process, right? We have an initial input, which in this case we're here, right? And we put it into the first function, these, and then we put it, whatever value that gave us, we put it into the outside function. Okay, wonderful. All right, so we've got the same functions here. Let me copy those down. Okay, so we want to find and simplify composite functions and also state the domain of each of these. So this is going to be probably the difficult part in these sections, or this section, excuse me, finding the domain of these things. So let's remember what it was that we were doing with composition. So I take my x value, and this is going to be, from the set of real numbers. This is some real number. We don't know if there's any restrictions on it. Our restrictions are going to come from what our functions are, right? So here's our function f, and out from the function f comes f of x, the function value, right? So f of x. Okay, so when we find the domain of composition, it's not just one function, right? I'm going to be plugging this value then into another function, g, and then the output from this one is going to be g of f of x. Okay, so let me just write down steps here. Let's say to find domain of g composed. Okay, because that's what we're going to be doing here, right? So the first thing we need to do is we need to start with all the real numbers, right? Because x is just some real number. We don't know what it is, but it's just some real number, right? And if I'm putting it into the function f, x needs to be in the domain of f. So first thing we want to do is find the domain of f. So find domain of f. Okay, so in this case, we can do this directly, right? Our function f here is a polynomial. We know that the domain of any polynomial function is all the real numbers, so we can do that without really any work, right? It's just some real number. There's no restrictions on f, and that is wonderful. Okay, so now our second step, well, that says we found the domain of f, so x went into f, and now it comes out, and now we've got a function value, f of x, some number, right? And it's going to be some number because we put in a value that's in the domain, right? Okay, so now we're putting the function f into the function g. So we need to know what the domain of g is. So let's find the domain of g. All right, so in this case, our function g is this one here. So the only restriction here is where radicands are negative. So we need x plus 3, which is the radicand, to be bigger than or equal to 0, right? We've seen this before. So we can solve that pretty quickly, x bigger than or equal to negative 3. And we can write this in either set builder notation, right? Set of all x. That's kind of ugly. So the set of all x, so that x plus 3 is greater than or equal to 0, which is the same as the set of all x, so that x is bigger than or equal to negative 3. Or we could write this as, the interval negative 3 to infinity. Okay, now here's going to be the hard part. So now we need f to be in the domain of g, right? The function f is going into the function g. So we need to remove from domain in 1, so the domain of f, all x, so that f of x isn't in the domain of g. Okay, so we would just want to remove all of the x values so that our function value is not in that set. Another way to do this with, or another way to phrase this with a radical is that we need, in our case here, our function value to be bigger than or equal to negative 3, right? Because if I'm going to put in an x value into f, it can be any real number, but then when I'm putting the number into that function g, we need that to be bigger than or equal to negative 3, right? So in a case with a radical, we can just solve this thing, right? So we know what our function f was, x squared minus 4x. So I need the function f to be bigger than or equal to negative 3, and we can solve this for x. Okay, so we would do this in, air quotes, the usual way, because we've done this a bunch of times, right? We're solving a polynomial inequality, so we want to get everything on one side. We want to factor everything. We want to put our zeros on a number line. We want to use test points if we need to, right? Put in 0, put in 2, put in 3. So we get zeros here, right? We're just doing our number line business. If we put in 0, we're going to have a positive over here, right? Negative times negative. If I put 2, the number 2 in here, 2 minus 3, that's negative. 2 minus 1, that's positive. So this is going to be a negative value. If I put 3 in there, both of those, or excuse me, I should put a 4 in there for a test value, something bigger than 3. Both of those numbers are going to be positive, so we need that. So what this tells us is that our wherever this thing is positive, so negative infinity to 1, and we want where it's equal to 0, and then we want everything else where it's positive. So here is our domain in this case. This makes it so our function value from f is in the domain of g. So here's our domain of our beautiful function. So that's definitely the hard part here, because if we want to go and and actually find our composition. We've got g of f of x. This is g of x squared minus 4x. And then we can just put this object wherever we see x in the function g, remembering what g was, 2 minus square root x plus 3. So 2 minus square root x plus 3. And we can go ahead and simplify this as well. So at this point, we might say, well, hey, why didn't I just do this first? Because I ended up solving that same thing there anyway, right? It's the same thing, right? When we have fractions, we might end up covering up some domain restrictions. So it would be advisable for us to find these domains first. And I mean, we can cross-reference ourselves and see if we agree once we get the simplified function value. And we could totally do that. But it's going to be in your best interest to find the domain of the function composition first. So, okay, good. We did the first one. That was g of f. Let me erase this real quick. Okay, so we erased that, and now we want to do part B. So now we want f of g of x. So over here, I just rearranged all these things. I just put f where g was and g where f was, because that's the arrangement we're going to be doing now. So it's still the same steps. We're going to, thinking about our little journey that x is going to go along with our little machine diagram, x is going to go into g first. So we need to find the domain of g first. Well, it's going to be the same as it was before, right? It's still the same function, so we have negative 3 to infinity. Our numbers have to be bigger than negative 3. Okay, then we find the domain of f, which is the second function we're going to go into. So the domain of f, again, f is a polynomial, so it has all the real numbers for domain. So then we want to remove from the domain of from the domain of the one we started with, remove from the domain of g, so what we start with, any value of x so that the function value from g is not in the domain of f. So in this step, we would say, oh, wait a minute, the function f has domain all the real numbers, so there aren't going to be any further restrictions. So our domain is just going to be the domain of g. Okay, right, because f is polynomial. We put any number we want in there. As long as we have a real number output from g, the value that we're going to be plugging into f is going to be real. So it works. So great, we found the domain, and we can find and simplify the composite functions. So if we want to do f composed with g of x, this is f at 2 minus square root x plus 3. And then we would just put that wherever we see x in the function f. Now the function f was x squared plus 4x, was it? Yeah, minus 4x, excuse me. And there we go. So, I mean, there's a little bit more here to do with our simplification piece, right? We just have to square this, multiply everything through by 4, then combine all of our like terms. But we can do that, and I don't think that nothing really new is being added by carrying out these operations. But we can do this, right? We can square a binomial. We can multiply things by 4. We can combine like terms. That's not exactly the difficulty of these problems. The difficulty is going to be finding the domains. So let's abandon this one for now, and we can go look at the ones with fractions, because the ones with fractions usually give us trouble. I mean, we usually have trouble with radicals and fractions, just in general. But let's take a look at the next one here. So we want now h composed with F. So let me rearrange all these letters in the definitions, or excuse me, all the letters in the steps here. Okay, there we go. So now we want to do part C, h of f of x. So let's find the domain first. So we want to find the domain of h of f of x. So again, with our little diagram here, our x is going to go into the function f first. So that's going to be our first restriction. So any restrictions from the domain of f, well, it's still a polynomial function, so it's still got all the real numbers for a domain, and that's super. Okay, now we want to find the domain of h. Now, after we get out of the function f, we've got a function value here, and it's going to get put into the function h, so we need to have the domain of h. Well, h here is a rational function. We know that all the rational functions have domain where denominators are not 0. So in this case, it's the set of all x so that x can't be -1. And if we want to, we can write that in interval notation, and that's wonderful. But this is our domain of h. Okay, so we have to remove from the domain of f all the x values that are going to make it so f of x isn't in the domain of h. So saying that in a slightly different way, where's my pen here? We can't have f be equal to the domain restriction from h, right? So we have to take that value out. So we're starting with all the real numbers, and we're saying, hey, I can have everything except for what gives me a function value of -1, because that's not in the domain of h. Okay, so let's find out where that is. We got our function f, and we want to find out where that's equal to -1. So we can do that. We've got x squared minus 4x plus 1 equals 0. We really want to factor, but if we can't factor, that's unfortunate. But hey, we can still use that nice quadratic formula, right? X is -b, so that's 4, plus or minus the square root of b squared minus 4 times a times c over 2 times a. And then we play the simplification game. We got 2 plus or minus the square root of 12 over 2. So that's 4 plus or minus 2 square root of 3, right, over 2. So this is 2 plus or minus square root of 3. Okay, so these values we cannot have in our domain. So we're going to remove from the initial domain of f, which was all the real numbers. We're going to remove all the values so that the function value from f is not in the domain of g. So we just found those, right? We just found where the function value of f is not in the domain of g. So our domain of the whole thing, and this was h composed with f, this is the set of all x so that x can't be these values. And again, we can write this as an interval, and that's fine, but that's not exactly the point here. So yeah, we can write this as an interval if we need to, but this is probably good for our purposes right now. Okay, something I guess to notice, or something maybe I could point out, is that what we're going to want to do is we're going to want to look at both of these, and we're going to say, oh, I'm just going to combine those, right? So combining those, we would just have x not equal 1. Well, x equal -1 is a value that we can put into this function, isn't it? So if I do, let's get rid of this. If we do h of f of -1, we can do this, right? Just to show us that -1 is in the domain of the composition. H of f of -1, so that's going to be, let's do a little scratch work up here. F of -1, yikes. So we've got -1 square minus 4 times -1. So this is 1 plus 4 is 5, so h of 5. And h of 5 would be 2 times 5 over 5 plus 1, so that's 10 over 6, which is 5 over 3. So -1 is in the domain of the composition. It certainly isn't in the domain of just the function h, but it is in the composition domain. Now, hopefully that cleared up what we were doing in this step. Okay, so I think we've got one more here. Yeah, we do. H of x. So again, let me erase this stuff. Okay, so now we're on to part D here. We want to find and simplify the composite function and then state the domain of each. Okay, so we're going to find the domain first. We could do this the same way we did it for these other ones. It might be a little weird because both of our functions are h, but we can sure still do it, right? So our first step is we're going to find the domain of h. This is the inside function, right? The h of x, right? So we're finding the domain of the inside function first. Okay, well, we know what the domain of h is. This is everything except for -1. Great. Second, we're going to find the domain of h. And this is the outside function, right? This function h. So the domain of h, again, everything except for -1. Okay, so we started out with the domain of h, right? We can't have -1. And now, the third step, we cannot have h of x be a domain restriction from h. So what that says is that h of x cannot be -1. Okay, now we just need to find out where it is -1. So we can solve h of x equal -1. Okay, h was 2x over x plus 1 equal -1. And we can solve this pretty quickly here, right? So as long as our x value isn't -1, this is a legal move, and we can multiply both sides by x plus 1 just to solve this rational equation here. So on the left-hand side, that denominator cancels out. We just have 2x. And on the right-hand side, we can multiply that -1 through. So we got -x minus 1. Okay, now we want to combine like terms, so adding the x to both sides. Now we can divide by 3. And here we have another domain restriction. So we start with the domain of our inside function. So that would be everything except for -1. And we have to further restrict ourselves so that the function value is not equal to -1. So there we have it. We've got our domain. And now we can write this as an interval if we want to. Right? We could do, write it as an interval if you want to. -1 union -1 to -1/3 union -1/3 to infinity. And we can write that. So we not only had to take out x equal -1 because that's the first function value we're going to go through. We can't have -1. And then we're going to also have to restrict that value -1/3. Well, because that's what makes our function equal to the domain restriction. Okay, so now we need to do the rest of this. We needed to find h of x and simplify it. So in doing this, we're going to show why it's a good idea to find our domain first. So finding this h of x, we know here's h, right? So we've got h of h. So we've got everywhere we see x in h, we're going to put h. Okay, that's great. Now it's a complex fraction, so we've got to simplify the complex fraction. So we can multiply everything by x plus 1 over x plus 1, right? Because we know that x can't be -1. All right, now multiplying this through, what's going to happen here? Well, in the numerator, this x plus 1 is going to cancel. In the denominator, it's going to cancel for that term, but not that term. So in the numerator, we got, looks like 4x, right? 2 times 2 is 4. And we got that x hanging out. And then the denominator, this first one here is going to cancel the denominator, so we just have 2x. And then the second one, we're going to have x plus 1. Okay, so we got 4x over 3x plus 1. So here is our simplified composition, and we can write that that's h composed with h at x. So something to notice here is that the domain restriction that we came up with here, right, we had to take out negative 1/3, that is still present in our simplified fraction. However, the other domain restriction that we had, namely the negative 1, that got canceled out when we were in the process of simplifying this. So word to the wise here, it is a better idea to go ahead and find your domains first so that we're not covering up those domain restrictions with our other work, simplifying. Okay, super. All right, here we got a couple more problem types here. We want to write a function as a composition of two non-identity functions. So an identity function, let's just talk about this for a minute. Identity function, we remember that was just this one, right? And we called it the identity function because whatever the input is also going to be the output, right? We're going to get back whatever we put in there. So, if I do f of 2, that's just 2, right? F of negative 17 is negative 17, right? Because it's just giving you back the output. So the reason why we don't want to do this, or the reason why they don't want identity functions in here, is because it's trivial, right? If I want to find g composed with f of x, and I want that to be square root of 5x minus 1, well, why don't I just say g of x is x, and then f of x could be square root 5x minus 1? Because then when I put f inside of g to do g of f, this is g of square root 5x minus 1. Well, that's just square root 5x minus 1, right? Because g is the identity function. So we want to stay away from making the exercises trivial. So we want to stay away from the identity function. Okay, so we want two non-identity functions so that their composition is this one. I guess one of the things that a piece of advice would be to maybe not think about it too terribly hard. Think about the general structure of what this looks like. So it's the square root of some stuff. Well, what if we said that our inside function was just that stuff, right? So f of x is 5x minus 1. And then what would g have to be? Well, if I'm going to plug 5x minus 1 in and I'm going to get this, I'm going to have square root of x. So we can absolutely go and check this. We can probably check this pretty easily mentally, right? Put this 5x minus 1 in that position, and we do get what we had. So part of the difficulty, I think, on questions like these are thinking about them too much. Or maybe not recognizing that there's a whole bunch of different ways that we could do this. So if I wanted to, I could say that the inside function was 5x, and then g would have to be square root x minus 1. So now when I put f inside of g, we're going to get that function that we wanted. So here's two different examples of the way this one could play out. So the part B here, that was part A. Part B here is much the same, right? So we kind of look at the structure of the thing and we say, well, make the inside function be as simple as possible without just making it be the identity. Well, we're probably going to choose x squared. If I let f be x squared, then what would g have to be? Well, looking at the structure of this, if I'm going to put x squared wherever I see x, that's just going to be my g, right? 2x minus 1 over x plus 3. So now if I put x square in for x here and here, it looks like the composition, and we're good to go. Okay, so yeah, part of the difficulty on these is probably thinking about it a little too much, or part of another difficulty might be our temptation to use the identity function, but that kind of trivializes the problem, and we shouldn't really do that. Okay, so that's wonderful, and that's it for this section 5.1. So yeah, have a great rest of your day. Thanks for watching the video.